Hey physics, let's do some quick energy review, okay? So remember when we're talking about energy, energy is always conserved. And so we can say that if you have the energy of a system, no matter what's happening, whatever energy you start with, after that action is done, or like when something changes, whatever energy you start with, you have to also end with that same amount of energy. Okay, when we're talking about this, we're talking about mechanical energy. So there's three different kinds of mechanical energy that we've talked about. There's the energy of motion, which is E kinetic. Okay, so kinetic energy. There is energy of gravitational potential energy, or gravitational positional energy, or EG. And then there's the elastic energies, or the spring energy, okay? So if you're in doubt and you're like, okay, I know I have to have I have to think about what these three kinds of energy are doing before anything else happens, okay? Whatever you have on this side, so this is the before situation, so we'll call this K1, G1, S1. It's going to equal the sum of all these things added up at the end, okay? So this is G1, and this is, 2, and S2. So let's say we have a slinky, no, it's not a slinky. Let's say we have a really, really tight spring, okay? And okay, my cat's trying to get in the way. Back off, cat. Let's say we have this spring, and we squish it down. So we have this spring that we've squished down, okay? And if we let it go, it's going to push a marble. So if you've ever played pinball, it's like that. So we've squished this spring all the way down, and let's say we squished it 2 meters. It's a really big spring, okay? And let's say that this marble, let's say it's a bowling ball that weighs 10 kilograms, okay? So we let it squish down, and then we let it go, and the spring goes boop, and the ball goes, whoa, my God, in that direction, okay? And it goes up. Okay, so what I want to know is how fast does that ball go as soon as it leaves that spring? What's the maximum velocity it goes, okay? And you could think about it, it could be going sideways too, it doesn't actually matter. Actually, in fact, why don't we think about it that way? Let's think about them going sideways. So let's do it this way. So we have this spring, we let the spring go, and then all of a sudden the ball goes shooting off in that direction, sideways, okay? So the height never changes. Oh, that's my cat. Thanks, cat. Thank you. Okay, so that's our situation. So what happens first? So before anything happens, when the spring is squished, okay, let's redraw this a little bit. So let's do it over here. So here's our floor. Here's our spring that's squished. Here's the ball that we're going to push, okay? So in the before situation, it's not moving yet. So if we think about before, our EK1 plus our EG1 plus our ES, okay, 1. What's happening? So it's not moving, so there's no kinetic energy. It's not at a height, it's on a table or whatever, so there's no gravitational potential energy, but there is spring energy. Okay, so there's spring, the spring energy is given as 1/2 kx squared, and it is annoying that it's a k considering that kinetic energy is k, but we just roll with it, okay? Just so you know, if it's in an equation, we're talking about the spring constant. Okay, so this is the spring constant. So that's how squishy this spring is. How good of a spring is this, okay? So if we have this situation, well then after we let go of that spring, all of a sudden it's going to go bloop, and it's going to push that ball in that direction. Okay, so how fast is that ball going at the end of this situation? Well, again, we'll say, let's take stock, let's figure out what energy we have. So we have, we can talk about kinetic energy, we can talk about the gravitational potential energy, and we can talk about the spring energy, or the elastic energy. Okay, well, the kinetic energy is definitely present because it's moving. So, and you know that this has to equal that. Okay, the before has to equal the after. The total before has to equal the total after. Okay, so we're going to put an equal sign. So there is kinetic energy here because it's moving. So I'm going to say that's 1/2 mv squared. It doesn't have a height. It's still, even though I drew this badly, it's still racing on that ground. Okay, so there is no gravitational energy. And is there spring energy? No, it's already off the spring. So the spring has given up all of its energy. Okay, so then we can see, oh, look at that. Since I took stock of what energies I had on this side and what energies I had on this side, I can figure out the equation, okay? So the equation I'm going to use is 1/2 kx squared equals 1/2 mv squared, Okay, so the bowling ball we said is 10 kilograms. Okay, so let's see. I have one. Oh, what am I solving for? I'm solving for velocity. Let's say that we're given that that spring has a K of, did I give one? No, let's say it's 0.1. Okay, and let's think about what that is. So if it's K, what is that? It's going to be meters squared per per joule, and we'll get to it. Okay, we'll get to it in a second. So let's say we want it to be 0.1, 0.1. Okay, that's K. We said that we squished it 2 meters. So 2, oh, but that's meters, and that's squared. And then we say, okay, so 1/2, we said the mass is 10 kilograms. We don't have to do anything to that because it's in kilograms, and we like that. And then we're solving for V. Okay, but remember, V is squared. Okay, so I have 1/2 times 0.1 times 2 squared. So 2 squared is 4, times 0.1 is 0.4, divided by 2 is 0.2. So 0.2 equals 1/2 of 10, so I'm going to write that as 5V squared. 5 kilograms, V squared. Now I'm going to divide both sides by 5 kilograms. 5 kilograms. Oh, look at that. Look at that. I did not. This is kilogram. What is this? Kilogram meters is what that is. Okay, kilogram meters per second squared. Seconds per milligrams seconds. That's what it is. Okay. Then we say, okay, I'm going to divide. I'm going to do 0.2 divided by 5. No, that's not what that unit is. Okay, I'm going to look up what that unit is. I'm the worst. You'd be given, oh, it's Newton meters. That's what it is. Newton meters, right? Anyway, 0.2 divided by 5, okay? That's going to be 0.04, and we end up with meters squared per second squared, okay? Because on this side we have that, on this side we have V squared. Now I'm going to take the square root of both sides. I'm going to figure out how fast this thing is going. So square root, velocity is 0.2 meters per second. So that's how fast it was going. So there's not enough, I mean, that's a reasonable number, okay? So there is our answer. That's how you would figure out what's happening here. So that's not the only kind of energy problem we can have. We can have problems where it's like, hey, if you start, if you're rolling down a hill or if you drop something, okay, and you start 10 meters high and you're moving... yeah, if we want to find the velocity before you hit the ground, like the moment before you hit the ground, if you have some object, let's say that object is 5 kilograms, how fast are you moving when you hit the ground? Oh no, well let's think about this again. What do we have to start? Let's talk about the spring plus the kinetic energy plus the gravitational energy is going to equal, at the beginning, is going to equal the spring plus the kinetic plus the gravitational at the end. Well, there's no spring. We're just dropping something. Okay, so that's 0. The kinetic energy, as soon as the second you start it dropping, it's not moving yet. Okay, so that's 0. And then we say, oh, and then we have the energy of gravitation. Oh, there is a height here. So we do have a gravitational positional energy. And remember, we can describe this as either FGH or if you're on Earth, MGH. And we deal a lot in this class mostly with Earth and not orbits, so you can go with that. So I'm going to use this one because this is my favorite kind of gravitational potential energy equation. And so I'm going to get that means this is mass times the acceleration due to gravity, which is 9.81, times the height, okay? On the other side, again, there's no spring energy. It is moving, so we're going to put in for EK 1/2 mv squared. And it's going to have a height of 0, so there's no gravitational energy. So that's 0 too. So what are we left with? We're left with mgh equals 1/2 mv squared. Cool. So if you look at this, you might say, oh, I could divide both sides by mass, and then the mass is gone. Or if you don't notice that, you could just go ahead and plug in from here. So mass, we said, is 5 kilograms. The G is the acceleration due to gravity, and it's always 9.81 meters per second squared if you're on Earth. And then the height, we said, is 10 meters. I did not leave myself enough room. But then we have that equals, I'm going to put it on this side, 1/2, so that's this. That's over here. So 1/2 times the mass, which is 5 kilograms, times velocity squared. So now let's simplify both sides. So 1/2 times 5 is 2.5 kilograms times velocity squared. is 5 times 10 times 9.8. So it's going to be 50 times 9.8. Please remember your calculators for the quiz tomorrow, you guys. Oh my goodness. 5 times 9.8 times 10. So 490. And what's my unit? It's kilogram meters squared over second squared. Kilogram meters squared over second squared. Cool. So that's weird, but that's okay. I'm going to divide both by 2.5 kilograms. Kilograms. Oh, look, then the kilograms will cancel, and then this whole thing cancels. So 490 divided by 2.5. So we get V squared is 196 meters squared per second squared. Okay? And then you just take the square root of both sides. V is the square root of that is, come on, calculator, wake up. Come on. Ugh, you guys. Why is my calculator not focused? You guys, are you yelling the answer at me right now? I bet you are. 196 square root 14. So I made these numbers up completely, and it came out to a nice happy number. 14 meters per second. Okay, that's how fast I would be going before it hits the ground. Yay! Now remember, we also talked about, do you have enough energy to get something done? So if I wanted to secretly hit something with that ball that we hang from the ceiling, let's say I really wanted to hit this laptop. Okay, let's say there's a laptop on a stool, and I just really want a new laptop, so I'm like, I'm going to hit it with this, and then I'm going to get a new laptop. But I don't want anyone to notice that I did it, so I only pull the ball back to right here. Okay? If I just pull the ball back to here, how high will it go on the other side? Well, it's only going to go as high as you originally give it. So let's say this is 2 meters and the laptop is 3 meters. Can I pull it back only to 2 meters and have it hit 3 meters? No, because it's only going to go as high as you originally give it that energy for. And so it's only going to go that high. So it's going to miss it by a whole meter. Okay? So think about that kind of thing. Yeah, you're going to do great. Make sure you look at your impulse stuff. Remember that impulse is delta P is fat mass. It's force times T is going to equal mass times delta V. Just make sure you remember how to plug these things in. You guys talked about this. You should know all about it. And I'll see you guys tomorrow. Bye.